What's up, folks? On today's episode, like we said, we're talking about a new version of wearable healthcare devices that don't rely on batteries. They actually rely on your body heat to help keep them alive. Personally, as an Apple Watch user, I would say my biggest complaint with the Apple Watch, and I don't have many. I've been an avid Apple Watch user for the last 7 years. And my original
You sold me on
Gen
it,
1
so.
Apple Watch is still kicking. Sold for Bode on it. Sold
Yeah.
Nelly on it. I'm an apologist, but if there were one thing I were to pick on, it would be the battery life. Like, I love this thing. I love the fact that it can track my health around the clock. But for me, the concern is I can't track it around the clock when I've got to take this, watch off my wrist and hook it up to a charger instead. So, pretty interesting challenge here that this team from Carnegie Mellon University is attacking. And I think they've got a really interesting approach as well.
Yeah, it's funny. I feel like this is becoming more and more of a trend. I don't remember exactly which episode it was, but at some point we were talking about a glucose monitor, also a wearable device for your health. And I think they were using the excess glucose in the system to actually power the device so that you no longer needed a battery. And it was like, the excess glucose is being used up so that you don't have to worry about it either, which was pretty cool. But now we're seeing, another form of, I guess, waste from our body, which is wasted heat being transferred into energy. I'm curious to see how they're accomplishing this.
Well, and it's not just waste, right? Your body is designed to generate heat, but it is waste in that we're not using it. We're not capturing this energy and using it for anything. So your body's going to generate heat whether you like it or not.
Might as well use it.
let's use this as a power source. A thermoelectric energy generator is the technology that they're using here, and the fundamental way that these thermoelectric energy generators work, which is a little bit interesting, is using a temperature delta from one side of the thermoelectric energy generator to the other to generate electric current. So it's a little interesting to note, just fundamentally from the start, that it works best when there's a high temperature delta from one side of the generator to the other. So one of the things that they mentioned is that this will work really, really well when the body's moving. So the body's generating a lot of heat. And then on the other side, there's convective cooling, meaning like that the opposite side, the outside of this device is extra, extra cool. I was thinking about other potential scenarios where it'd work really, really well. Like if I'm hot, I'm exercising and it's really cold outside, as a potential, pro, I think for them. A con I was thinking of is like, it's just very top of mind right now because I like to exercise. Nelly and I are running a lot, but it's also very hot outside.
That's exactly what I was going to say.
I'm wondering if it works well enough. It doesn't have to work perfectly. Does it work well enough to still power their sensors if I were to go on a run and I'm very hot and it's also a very hot day outside and there's very little temperature delta between my skin and the outer air temperature?
Well, that's exactly what I was thinking because I was like, like on a hot day, if you're running, then as your body heats up more and gets, closer to the outside temperature, well, actually, your body's probably, the interior temperature is quite a bit hotter, but still, as it gets closer to what it's like outside in Virginia where we live, which is usually like 90, 92 on the really hot summer days, it probably becomes less effective. Like the convection cooling that you get from running is probably going to be trivial at that point anyways. So I'm wondering how they would tackle that. But the analogy that I was thinking of in my head for how this technology works, this might be a little nerdy, was how lift is generated, like when you have low pressure, high pressure, and that's what you're kind of going for. So I was like, the delta for cold temperature, warm temperature is what we're aiming for here too.
No, I'm with you, and I don't know enough about the actual math equations of it, but I imagine that's a pretty good analogy here. One of the things that's really interesting, and I think is important to mention because we just kind of dogged on this idea for like the last 2 minutes, is generally speaking, comfortable room temperature for most people is somewhere in the realm of 70 to 75 degrees Fahrenheit. General body temperature of humans is around 95 to 98 degrees Fahrenheit. So we're saying generally there's about a 20 degree Fahrenheit difference, if not more, between your body and then the ambient air around it. So it's an awesome opportunity, again, for the vast majority of people during the vast majority of their day to be able to passively generate electricity based off of the temperature delta between their body and the surrounding air. And again, that's the way that this works, is it's focused on the delta between one side of the thermoelectric generator and the other, the hot side being the human body side and the cool side being the environment around it. But a couple of the challenges they experienced as compared to current thermoelectric generators is there was some concerns with flexibility. Are the current thermoelectric generators flexible enough that you would actually want to wear them and put them on your body? Or is it like a stiff, solid sheet? Those are the ones that I'm most familiar with. They look like an ultra thick playing card, essentially. They use stacks of metals to generate this electricity based on temperature deltas from one side to the other. So, would you like to strap an ultra thick, ultra stiff playing card made out of metal to your body? Probably not. What this team did is they worked using a liquid metal epoxy composite that enhanced the thermal conductivity, but also made it flexible and stretchable. And I thought that was really interesting, their use of flexible materials here. They did a lot of testing, similar to the stuff that you and I did when we were working on flexible electronics back in college.
Man, the good old days.
They stretched them, they twisted them, and they did this over a lot of cycles and ensured that even over time, this flexible substrate works very, very well. It's got a really high power density, actually improved power density by about a 40x factor compared to their previous design. So they're able to, using this liquid metal epoxy composite, get something that's not only flexible, but also with high thermal conductivity so that the energy generator portion of this works really, really well.
So this always threw me off when we were in college. But for the folks listening that are confused about power density, energy density is how much energy like your device can hold, right? Power density is the rate at which energy can be transferred. So when you have something that's doing a lot of processing, like an Apple Watch would, you want a high enough power density to do all those on-device calculations. And it looks like this is what their device is able to accomplish in comparison to their competitors.
Yeah, that's what I was going to mention right there. Is it's not energy density because they're not storing energy necessarily. Yep. Although perhaps they could have a battery on board to help store some energy.
Just in case.
But power density there, like you're mentioning, is related to the generation of electricity, the transfer of power. So the generation of electricity from the temperature delta, again, between your skin and the ambient air, that was about 40 times higher than previous state-of-the-art designs, which is really interesting.
Yeah. And I'm a big visual person. Looking at the little video they made on the WeWolfer article that we're going to be linking in the show notes, the design's pretty interesting. It kind of reminds me of like I've been watching a lot of the House of the Dragon and Game of Thrones. Those like gauntlets they used to wear back in the day to protect themselves. It's got these little patches of metal that's held together by a little wrist wrap. So Apple Watch is great, but this could be a fashionable alternative for those like me who yearn for the good old days of knights and whatnot.
Well, not just the medieval fashion sense that you have, but also just talking about this from a pure impact perspective, right? Any wearable healthcare device that uses a battery for power right now, some of the examples that they used on this specific prototype are a pulse oximetry sensor, which looks at your blood pulses as well as the percentage of blood oxygen dissolved in it. That's very similar, and it's actually the same sensors that they have in an Apple Watch or in my smart ring, etc. That's just one example, right? This is an analogy for a platform that can hold many different types of sensors. One of the examples that I thought of, and is actually mentioned in the article as well, is think about something like glucose monitoring. You mentioned it earlier as well. Or heartbeat monitoring, right? To make sure that you're not having any atrial fibrillation or anything like that, right? An inconvenience for someone with, a health tracker that's using it to better their health and track their activity can become a safety risk for folks who are using this to keep themselves alive. So if you need constant heartbeat monitoring, or if you need constant glucose monitoring, anytime you unplug your device to recharge it, that poses a significant risk for someone with a critical health condition. Right. So again, for me, it's an inconvenience. For someone else, it can become a significant risk to their health. Using something like this, having a cuff wrapped around your arm, may be worth the inconvenience, or in you're kind of making a jab at it, like the look of it looking like a medieval gauntlet. It may be worth that if it gets you continuous health monitoring without the risk of having to swap batteries or stop and recharge. If you're able to do this passively, right, your body generates this heat all on its own. I trust this team's ability to make it in like sleeker packaging, but two, I also think that that's a worthwhile trade-off, especially if you can do it in kind of like a incognito manner. Make it look like another part of an outfit or something like that. Make it look like a compression sleeve or something like that. I don't know. I see a lot of promise with this idea.
Yeah, I'm totally with you, man. And especially, I think you hit the nail on the head there for applications where it's not just a nice to have, like how I use my Apple Watch for tracking a workout, but it's a must have, and this is a life or death situation, like glucose monitors. This would be a great little tool. Now, I am wondering how much, when I think about an Apple Watch, it's what, like an inch squared. How much surface area would something like this take up to be able to operate like an Apple Watch or like a glucose monitor? Do you know? Because I don't think I could find it. Yeah, I couldn't find it on the article, but I am kind of curious about like how big it would have to be as of now, at least. And I wonder if that changes depending on where you put it on your body. Like, let's say what are the regions that generate a lot of heat? I'm guessing like your abdomen, maybe, because all the heat is in the center.
Well, I do know when you're hot, you've got a high level of blood flow in your hands and in your feet and in your face.
Okay.
Although I don't know if I'd want to wear this on my hands, my feet, or my face. So I know they tested both the chest and the wrist.
Uh-huh.
And in both of those, they saw higher output depending on the temperature differential. So it was very sensitive to that difference between the skin temperature and the ambient temperature, and if there was any type of convective cooling from being in motion. I imagine wrist being a really good application there because it's not going to be padded under layers and layers of clothing that would keep the cool side of this very warm, thus reducing its effectivity. I think a wrist could be a potential, at least, again, based on my elementary understanding of the fundamentals here, it could be a best potential application for this. And again, it would just look like a wrist sleeve or something like that.
Well, when you mentioned feet, my mind immediately went to socks. I could rock some smart socks, but I feel like washing that and then maintaining it might not be. And I don't know how much data you can get from your feet in comparison to like your heart rate that you can get from your wrist. So maybe not
your feet
the best.
Stank.
Hey, man, it's not true. Everyone, they do not.
It's gonna take a lot of work to defeat the allegations there. I'm sorry, my friend.
It is. You put me in a rough situation. We're gonna have to address this in a follow-up episode.
Well, I will say let's start to kind of wrap this up here. We've made a promise to our listeners, and it's good feedback. We got, what do we do to the haters? We love them. It's good feedback we got from one of the haters.
It didn't seem like you meant that, but okay.
We don't talk about the cons enough, so I want to talk about both the pros and the cons. Pros, very simple here. Idea of producing continuous power from body heat, not having to recharge a device. Again, I've harped on the inconvenience of having to recharge my Apple Watch. Imagine if that inconvenience was gone and I had a wearable device that had infinite battery life just due to my body heat being generated. That's awesome. I love the idea that it's really flexible and comfortable to wear. And I also love that they've tested this over thousands and thousands of cycles to prove that it's actually flexible and resilient to bends and twists and stretches, as opposed to just making an assumption there. Some cons, I know that this will require a bunch of development costs before it ever makes it to market. It'll require a lot more testing and refinement for commercial use. And one of the things that you mentioned that I also would love to see more information on is like, how does the power output from this device compare to the power consumption required for like colloquial devices? I just think it would help from a context perspective to say like, right now, this is just an example, but right now the device we have generates about 1/10 of the power needed to run an Apple Watch. But if we improve X, Y, and Z, maybe we can get to the power that an Apple Watch requires. I don't know if they're there yet, but I would love to see some type of comparison between, what does an Apple Watch need? What does a Fitbit need? What does a glucose monitor need versus what does our device already produce?
I don't know if this is the best analogy, but it makes me think of like solar panels. Like, how many solar panels would I need on my house to get the amount of energy I get right now from the grid, right?
Exactly, right? Yeah, power generation per surface area on your skin.
Yeah, that's what it made me think of. But yeah, that sounds good. Do you want to do a quick wrap up of what we talked about today?
Yeah, we'll do. Do you wish your health devices didn't need charging all the time? I do. I hate when my Apple Watch dies. And in this case, I'm excited from this research from Carnegie Mellon because they've introduced the first health device powered by body heat with no batteries needed. The device is powered by a thermoelectric generator. It uses your body heat on one side as a way of generating power in contrast with the cool side of the thermoelectric generator, which is exposed to ambient air. It works really, really well when you're moving and works really, really well when there's a difference between your skin and the ambient air temperatures. It's got smart sensors just like Apple Watches do. In my mind, it's all the things that you could want in a health device. Think about for glucose monitoring, for heartbeat monitoring, for other types of health tracking, but without the awful battery life that comes along with a lot of those devices today. I'm really excited about this being the future of health devices that never need to get plugged in and charged ever again.
As am I. That was money, man. Great job.
Thank you.
Folks, thank you so much for listening. And as always, we'll catch you in the next one.
Peace.